Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 5, Geometric Figures, Lesson 2, Do You See What I See? The directions in the Ready section say, consider the given statements and fill in the blank with something that makes sense. All right. The first comparison demonstrates a relationship. And the second comparison has a blank for you to fill in based on the relationship provided. There may be more than one logical way to fill in the blank. For example, in the statement, foot is to boot as hand is to blank, you would consider the first part of the statement, foot is to boot, and think about the relationship. It's apparent that a foot can go in or wear a boot. So logically then, it would make sense to fill in the gap with glove, since a hand can go in or wear a glove. So the first assigned problem was number 2. Question number 2 says, fishing is to lake as soccer is to blank. Okay, well, first thing we want to do is we want to figure out what is the relationship that is sort of apparent or evident, or however we want to think about it, in the first part of this sentence. So fishing is to lake. So what is the relationship between fishing and lake? Well, a lake is one area that someone could go fishing. Obviously, people could fish in a river, people could fish in the ocean, lots of different places that people could fish, but a lake is certainly one potential place. So fishing is to lake as soccer is to blank. All right, well, what is a place where someone may play soccer? Again, your answers here might be something different, but when I see this, I say to myself, all right, well, soccer is commonly played on a field. So fishing occurs on a lake and soccer occurs on a field. Next question. Question 3. Question 3, if you're looking at the screen right now and you're comparing it to what's in your book, the book version actually left out a couple of kind of key words. So what you're seeing on the screen right now is the version that we want to work with. So again, just notice that in the book, you may have been missing a couple of words here, but the screen version is the one that we want to work with. So for number 3, my sentence is equal slopes is to parallel lines, all right, as negative reciprocal slopes is to blank. All right. So this one's a bit more of a geometric context than the first one with fishing and soccer. So for number 3, we want to figure out, all right, what is the relationship in the first part, in the underlined in red? So equal slopes is to parallel lines. Well, parallel lines, the definition of parallel lines is that they will never intersect, okay? And we can indicate that with just like an arrow sort of somewhere on the line. And one thing that is true about parallel lines is that they have equal slopes. So if we'll call this line M and we'll call this line N. So if the slope of M is, let's say, 2/7, then the slope of line N is also 2/7. So parallel lines have equal slopes. Okay. So then the green part is basically then asking us, all right, well, if parallel lines have equal slopes, then what sort of lines have negative reciprocal slopes? Okay, so again, sticking with M and N here, I'll get rid of, I guess I'll get rid of N. and we'll just keep m the way that it is. Let's continue to assume that m has a slope of, let's say, 2/7. Well, if we have another line, we'll call it line P. Well, if m has a slope of 2/7, and if I want to look at the negative reciprocal of that, well, the negative of a positive is negative. And then the reciprocal means we flip a fraction. So here our fraction is 2/7, the numerator is 2, the denominator is 7. The reciprocal means that those are going to flip, which means now my numerator is 7 and my denominator is 2. And so it turns out that if line M has a slope of 2/7, and actually maybe I'll draw this a little bit differently so that it actually looks like it might have a slope of 2/7, so something like that. So line M in this case has a slope of 2/7. Negative 7/2 would actually look kind of like this, and this would be line P. Right? So again, here the slope is 2/7. Here the line is negative, or the slope is negative 7/2. And it turns out that when you have this situation, these lines form a right angle. So I'll indicate that with a box. And when two lines form a right angle, the word that we want to use there is perpendicular. Perpendicular lines. I guess I've left out the word line. Perpendicular lines. And that is our answer for number 3. Question 5. Subtraction is to addition as division is to blank. I think this one might be somewhat straightforward. So the first part of this sentence establishes the relationship that we're looking for. So subtraction is to addition. All right, well, what is the relationship between subtraction and addition? And I think most of us are pretty comfortable with the idea that subtraction and addition are inverse operations. Okay, they undo each other. If you have x plus 6 and you want to get x by itself, you subtract 6 because you want to get rid of plus 6, so you get rid of it by subtracting. So then if subtraction is the inverse operation of addition, then basically this question is saying, what is the inverse operation of division? How do I undo division? Or what is the operation that division undoes, right? They kind of undo each other, so you can look at it as in either direction. No matter how you look at it, I think we're pretty comfortable with the idea here that the inverse operation to division is multiplication. If you are dividing by 5 and you want to undo that, you can undo that by multiplying by 5. And that is our answer for number 6, or 5, number 5. Question 6. Congruent is to shapes as equal is to blank. Again, the first part of this sentence, the part that's underlined in red, that establishes the relationship that we want to sort of figure out or identify. So what's the relationship between congruent and shapes? Well, as we've talked about, congruent, which as a symbol is an equal sign with a tilde above it. So that's a symbol for congruent. And congruent is used to compare figures that are identical. So if we have two triangles, and those two triangles are identical, they're the same size, same shape, same side length, same angles, same area, same perimeter, same everything, just different letters and in a different spot, we can say that they are congruent. And unofficially, we can sort of think of congruent as the geometric equivalent to equal, right? You've been using equal signs in math for a long time to say that two Well, we're going to answer this in just a second, but when we use equal signs. But in geometry, we can't really say that a shape is equal to another shape, but we can say that a shape or a figure is congruent to another shape. So what's sort of the same sort of context in which you would use an equal sign? Well, you would use an equal sign to compare, say, numbers, right? 3 plus 4 equals 7. That tells us that 3 plus 4 is essentially the same thing as 7. They're quantitatively the same thing. So what we can say here for number 6 is equal to numbers. And since this is a geometric unit, the numbers are going to frequently pop up in terms of measurements of things. Measurements. Okay, so measurements could include side lengths, they could include angles, they could include area, perimeter, volume, anything like that. Anything that's a number, you can use an equal sign to compare them, but if it's a shape or a figure, you would want to use a congruent symbol. The next section, the directions say, decide if the following statements provide a true logical conclusion or if the statement is false. If false, provide a counterexample. Okay, so if it's true, it's true, and if it's false, we got to say it's false and also give a counterexample that would make the statement false. So question 7 says an acute triangle only needs to have one acute angle. All right. So as I think we've seen, when you're classifying triangles, there's sort of there's two ways of classifying triangles. You can classify them according to their angles, and you can classify them according to their side lengths. And there are relationships between those two ways of categorizing, but they are different. When you're categorizing according to side lengths, the 3 examples in that sort of bucket are equilateral, which means all 3 sides are the same, isosceles, which means at least 2 sides are the same, and scalene, which means all 3 sides are different. Now, that's not what we're talking about here for 7. For 7, we're talking about how are they classified according to their angles. And the way that triangles can be classified according to their angles are, you can have an acute triangle, you can have a right triangle, and you could have an obtuse triangle. Okay? Acute, right, and obtuse. So with an acute triangle, I'll just do maybe an example here, right? So this could be an acute triangle, and let's say our angle measurements are 50, 60, and say 70. Okay? So 50, 60, and 70. We could also have a right triangle. So with a right triangle, our angle measurements could be something like 90, and then we'll say maybe 40 and 50. And then with an obtuse triangle has an obtuse angle in it, so something like 110. And then our other angles could be, let's say, 30 and 40. Okay. So these are just a couple of examples of an acute triangle, a right triangle, and an obtuse triangle. And if you take a look at just these examples, there's actually a lot with our original statement that turns out to not be true. So with 7, and we'll just start typing here. So with 7, this is false. So we'll just kind of get that out of the way first. And let's sort of examine why this statement is false based on maybe some of our examples. So our original statement said an acute triangle only needs to have one acute angle. Um, well, if you take a look at our examples here for acute, right, and obtuse, the acute triangle has three angles that are acute. And as a reminder, acute means less than 90. So greater than 0, it's not a negative angle, but it's less than 90. A right angle equals 90, and an obtuse angle is greater than 90 but less than 180. So those are the three categories here for acute, right, and obtuse. So one of the reasons why this is false is if you take a look at the obtuse triangle, 110, 40, and 30, the obtuse triangle has two acute angles, 40 and 30. The right triangle also has two acute angles, the 50 and the 40. So kind of right off the bat, an acute triangle only needs to have one acute angle. Well, I mean, both the right and the obtuse triangles, they don't only have one, they have two, but they're not acute triangles. So if you take a look at the acute triangle, all three angles are acute. They're all less than 90. So it's not sufficient to say that an acute triangle only needs to have one acute angle, because it actually turns out that all triangles, regardless of what kind of triangle they are, all triangles have at least two acute angles. An acute triangle has two acute angles, a right triangle has two acute angles, and an obtuse triangle has two acute angles. So in order for a triangle to be acute, all three angles have to be acute. So we'll say all triangles have at least two acute angles, and acute triangles must have three acute angles. And so that is our answer for number 7. Number 8, if a rectangle is cut in half, then there will be two triangles. Okay, well, if we, over here on the right, if I draw a rectangle, I can see that if I cut this triangle, if I cut it along the line that is formed from the opposite vertices, from opposite corners, so if I do something like this, I am cutting the rectangle in half. So if we'll say this is a rectangle, so we'll go right angle, right angle, right angle, right angle. So that is a rectangle, and it is being cut in half. There will be two triangles. So for number 8, if I take my rectangle and I cut it in half in this, rather specific way, I will get two triangles. And then obviously, if I go the other two, that will also work, right? So if I go either top left to bottom right or bottom right to top left, I get two triangles in both of those cases. So you might be tempted to say that 8 is true, because we just saw it. The problem is number 8 is kind of being a little too confident in itself, I guess, because in order for 8 to be true, this would always need to be the case, right? So if you take any rectangle and you cut it in half in any way, that you will essentially always get two triangles. That's what this statement is saying. Now, going with a different rectangle is not a problem, right? If we have let's say we have a tall rectangle, right? That's actually not going to change much in terms of how we have to think about this problem, because again, if you go opposite corners here, you're going to get two triangles. So we're fine in terms of the type of rectangle. That part doesn't really make any difference. However, if we cut this triangle, now it has to be cut in half, but there's other ways of cutting this triangle in half. For the triangle that I just drew, this tall one, if we cut it like this, well, we're cutting it in half, but we are not left with two triangles. We're left with actually two more rectangles. So we have a rectangle up top and a rectangle at the bottom, and that is definitely not a triangle. So that alone is enough to cause number 8 to be incorrect. But there's lots of other ways that we could cut this. Obviously, we could also go vertically, right? That would cut it in half, and again, we're left with two rectangles. Um, you can also cut it in half like something like this, right? That is still cutting it in half. The two pieces of the rectangle are essentially congruent, and so this would still be cutting it in half. And in this case, you're definitely not left with two triangles. It turns out, well, you're clearly left with two quadrilaterals. It turns out that you're left with two trapezoids, two right trapezoids. But a trapezoid is still a quadrilateral. It's a four-sided figure, which is definitely not a triangle. Okay, so our answer here for number 8 is that this is false. So, okay. So this is false. And the reason why this is false is cutting the rectangle in half will only result in two triangles when cut along a line connecting opposite vertices or corners. Okay, that box will go away as soon as I'm done typing. So we'll cut along a line connecting opposite vertices. Go back to it. Okay. Any other cut will produce two quadrilaterals. And any other cut. Okay. So that's our answer for 8. Now, if your answer here was not exactly this, that's not necessarily a problem. I kind of included maybe a bit additional material that wouldn't strictly be necessary. All you really need you can either just indicate, as long as there's a single counterexample here, that is sufficient for this question. So just recognizing that there's lots of different ways of cutting a rectangle in half that do not result in two triangles. As long as you recognize that, I think that the phrasing that you use here for 8 should be sufficient, as long as you indicate, just give a counterexample, and that should be fine. Next assigned question was 10. If you have complementary angles, they will add up to 90 degrees. Well, this is going to be a pretty short explanation because this statement is true by definition. Complementary angles sum to 90 degrees. That's the definition of what complementary angles are. So for this question, there's not really a whole lot to do. It's really just essentially saying, do you know what the word complementary is in a geometric context? So if you were not familiar with complementary angles, then I could understand why 10 is confusing if you don't know that vocabulary word of complementary angles. But if you do know complementary angles, the definition is that they sum to 90. So this has to be true. There's really not a whole lot of wiggle room here. So yes, 10 is true by definition. Complementary angles do in fact sum to 90 degrees. Keep in mind, if the angles sum to 180 degrees, the word that we want to use for that is supplementary. So complementary sums to 90, supplementary sums to 180. Next questions are in the set section. Many diagrams have a history and progression to the way they are created. For each diagram, list the steps in the order that you think they occurred to make the diagram. Then make a conjecture about the piece of the diagram indicated. Consider using a compass and straight edge to reconstruct the diagram as you work. Finally, write an argument that can be used to justify to someone that your conjecture would be true. So for 11, our figure is that. And again, our task here is to list the steps that one could take to sort of recreate this thing from scratch. Once we're done that, we want to say something about quadrilateral ACED, which is, maybe I'll do this in a slightly, we'll use a 3. So ACED. So we're going to make a conjecture about, that's AC, CE, ED, and DA. So when all said and done, we're going to make some conjecture about that quadrilateral, and then we have to justify that conjecture. All right. So if any of you out there took a look at this problem and you took a look at this diagram and you were like, oh, heck no, I've got circles overlapping with other circles, and I've got letters and shapes and lines, and I'm like, no, you know what? I'm just going to go to the video, and we're just going to sort of like figure out how to do this. That's fine. That's why we're here. If you told me that this problem looks complicated, I could buy that. However, I do think that despite its sort of complexity, I do actually think that listing the steps to create the diagram is maybe a little bit less intimidating than it might seem at first. So basically with this question, what you want to do is you want to say, all right, well, if you had to recreate this picture, what would you do, right? You're given a blank sheet of paper. What would you do, right? And for me, I would probably start by just drawing a circle, and might as well go in like, I guess alphabetical order. So circle A is the circle that is centered at A. So it's this guy right there. Okay. So what I'm going to do over here on the right is I'm going to draw that circle. And my center is right there, and that center is A. I also notice that related to this circle, we have a radius that goes from A kind of up like this. And it intersects the circle at that point right there, which is point C. And there's also another radius going down, and that intercepts the circle at that point, which we can label as D. So I am going to start that. I'm going to start writing out the directions here that we are doing, and hopefully the formatting here is not going to be a nightmare, but we'll find out. So for step 1, we are going to construct circle A. I'll fix the box in just a second. I'm going to get all the words out, then I'm going to fix the box. So one says construct circle A, and radii, and as a reminder, radii is the plural of radius. You don't want to say radiuses. You want to say radii. Construct circle A and radii AC and AD. So if I wanted to recreate the figure that is on the left here, I think that one sort of reasonable way to get started is to construct circle A and then draw my 2 radii. All right. we should have a line over the AC and the AD because I don't have access to my fancy math you know fonts and typing here. I'm just going to do all that at the end. So I'm going to wait on any sort of other symbols like the line segment stuff until we're done listing all the steps. So step 1 is construct circle A and radii AC and AD. All right. So then what would I do? Well, I'm noticing in my figure on the left that point C, it certainly looks like it's the center of another circle, right? It looks to me like C is the center of this circle right here. So what I'm going to do is I'm going to now, over here on the right, I'm going to draw that circle. Notice that that circle intersects A, right? It goes right through A. So when I redraw this, I just have to be careful that I do that. This might be a little bit tricky. If you have access to a compass, this is going to make your job a lot easier. I'm doing this freehand, not really by choice, but because I'm on the rig and I don't really know how to use a compass on this thing. So hopefully this isn't a disaster. Let's see what this is going to look like. We're gonna hit A. All right, let's just do it. So I'm gonna go through A, past D, over there, and that circle is definitely not centered at C. Let's try that one more time, see if we can do a little bit better of a job. So it's going to be centered at C. All right, so let's go. I think my problem is D is a little bit too far down, but it's all right. We'll just make it work as best we can. That's going to have to be good enough for right now. Again, C is not really centered, but I'm doing this freehand. So anyway, all the more reason here, guys, to use a compass when you're drawing this. So don't be like me and draw it freehand. Use some of the tools at your disposal. So it looks to me like I've got a circle that is quote-unquote centered at C. And then I have another circle. We'll use a thicker line here. In my original picture, I have another circle that appears to be centered at D. We've got this guy. Right? So the circle in black here is centered at D. So let's see if we can do this without it being a disaster. It's above C. All right, so let's go, and again, notice that this circle goes through A. Okay, so it's going to look something like this, perhaps. Definitely not centered at D. But you know what? I think we get the point, right? So even though my centerings are less than ideal here, if I wasn't doing this freehand, I think that we could do this in a significantly better way. But I think that is at least sufficient for our purposes here. We don't really technically even need to be redrawing it right now. What we're really trying to do is list the steps, right? So our drawing isn't perfect, but what matters is listing the steps. So I'm gonna go to that right now because that's gonna look fine. So go away. Don't want that. I want to get back. There we go. So our second step here was we constructed circles congruent to A with centers at C and D. And I know that they're congruent because any circles that have the same radius length are congruent. That's all you need in order for circles to be congruent. If they have if the length of the radius or the radii are the same, then the circles are congruent. That's equivalent to saying if the diameters are congruent, then the circles are congruent. And so both of these circles that I just drew, the green circle and the black circle, are theoretically centered at C and D, respectively. And the radius of my green circle, well, it starts at C and goes to A. That's the same radius as starting at A and going to C. Likewise, for the black circle, the radius starts at D and goes to A. So therefore, it's the same thing as the red circle, which is A to D. So these are congruent circles. All right, well, the only other things that I really need to add here is there's this point of intersection on the right there. And that point is labeled as E. And not only is it labeled as E, but we also have these line segments that are connecting C and E, like that, and also D and E, like that. Okay, so let's go ahead and describe doing that. So our third step here is to construct point E at the intersection of circles C and D. And really, I guess it's the second point of intersection because the circles C and D also intersected at A, which we've already sort of labeled and sort of dealt with. But then there's this second point of intersection on the right, this point E. So we label it and we we constructed it. Oh, I guess we combined a couple steps here because then the next step is to construct the segments CE and DE. So step 3 was actually just identifying point E, and then step 4 was to then connect CE and DE. And our sketch is not perfect, but it got the job done. And now I think what I'm going to do, so that's everything that's in the picture, right? So notice the picture on the left, picture on the right, more or less our picture is done. I'm going to erase it because now it's bothering me because it's not like perfect. And I'm going to get rid of all this other stuff as well. All right, so now we're going to go back to the original picture, which looks a little bit nicer. A conjecture about the quadrilateral ACED, which again it's the only quadrilateral in this picture. And notice that it kind of looks to me like a diamond, right? And another name for a diamond, especially in geometry, is that I would say that a reasonable conjecture here is that ACDE is A. Now you could say a diamond, but if you want to use maybe even fancier math vocab, another name for a diamond is a rhombus. Rhombus. So to me, I think that that's a reasonable conjecture to make because it looks like a diamond. And actually, before I forget, let me go ahead and add, as promised, so we need a line over AC, we need a line segment rather over AD, line segment over CE, line segment over DE, and that's everything from the first part. All right, so just don't forget those line segments. Our conjecture is that ACED kind of looks like a diamond, which means it's a rhombus. So this is an opportunity to maybe reflect or remind ourselves as to what a rhombus is. A rhombus, so a rhombus, which again is also called a diamond, is a quadrilateral that has 4 congruent sides. Okay, so that's a rhombus. And then just as a real quick reminder, compare that to this shape, which I think we can recognize is a rectangle. The definition of a rectangle is that it is a quadrilateral with 4 equal angles. And I think that if you see that if you combine these two things into one quadrilateral, like this, if you take both a rhombus and a rectangle, well, it's a rhombus, so it has 4 congruent sides. It's a rectangle, so it has 4 congruent angles. And this shape, as you've known now for a while, is called a square. But little review there of some geometric terms. So it looks to me like ACED in this is the original figure is a rhombus. Now we have to justify that. Well, notice that in our construction, we drew a whole bunch of radii, and in order for this to be a rhombus, all 4 of the sides need to be the same. Well, we know pretty much for a fact that AC in the top left and AD in the top right, they have to be congruent to each other because AC and AD are both radii of circle A. So they start at A and they go out to the circle. That every radius of a circle is congruent, like within one circle. Any radius you draw is going to always be the same length. So AC has to be congruent to AD. Also, when we drew the circle centered at C, notice that CA, right? So notice that this piece right here it's a radius of the circle on the left centered at A, but it's also a radius of the circle centered at C, which means any other radius of this circle has to be congruent to CA. Again, any radius within one circle is going to be congruent to any other radius in that circle. So CE has to also be congruent to CA because they're both the radius of the same circle. Similarly, with this triangle, I'm just doing everything in green at the moment. So with the circle centered at D, well, DA is a radius, DE is also a radius, and so those have to be congruent. So it turns out, get rid of everything else here, it turns out that all of these side lengths of the quadrilateral are in fact congruent because they're all essentially the same radius. So now we just need to say that. So since AC and AD are radii for the same circle, they are congruent. I'll fix the box here. So just want to move this thing. There we go. Okay. So since AC and AD are radii for the same circle, they have to be congruent. Since circles C and D are constructed congruent to circle A, then their radii are congruent to those in circle A, because the circles themselves are congruent, which means the radii are congruent. So therefore, CE and DE are congruent to the radii for circle A, and all of the segments are congruent for quadrilateral ACED, which is the definition of a rhombus. And so that is our justification. Let me just go through. We just need little line segments over AC, AD, CE, and DE. And that's our answer for this problem. So again, not the easiest problem we've done in this class. You really do have to kind of think about it a little bit. I'll get rid of all this other extra stuff here. Don't need it anymore. So if you struggled a little bit with this problem, it's fine. It's why we're here to learn. But just try to, if you ever see a problem like this that's maybe a little bit, a couple extra steps here, kind of break it down, see what you know. And again, as we saw, if your sketch is not perfect, it's fine, because mine was far from perfect, but it got the job done. Next set of directions say, examine the diagram and add any information that is given to the diagram. Make a plan for finding the value of x. Follow your plan. Show your work, justifying the results. All right. So for question 13, we are told that the measure of angle C is equal to 90 degrees. And we have a figure here, the triangle, we know that one side is 10 centimeters, we know that another side is 26 centimeters, we do not know the third side, and we are being asked to find the length of that third side of this triangle. So even if the directions did not say to include, what we're given in the picture, you're going to want to do that anyway. So again, they tell us to include it, but even if they didn't tell us to include it, it makes sense that we would indicate that the measure of angle C is 90. I'm now realizing that they did not label A, B, or they didn't label any of the letters here, so I think we have to just come up with them ourselves. I wonder if that's a typo. But out of these three angles, the only angle that looks like it could be 90 is down here, right? So that kind of has to be C. And I could write 90, but I also know that 90 degrees is a right angle, and we can indicate a right angle with a box. So I could put like the number 90 there, 90 degrees, but I think it's actually going to be better if we just use a box to indicate that angle is in fact a right angle. And I don't think we're going to need this, but I'll just go ahead and say that can be A and that can be B. It's fine. I don't think it's going to matter. All right, so that's all the information that we're given that wasn't in the picture already, and we want to solve for x. So what we have here is we have a triangle. Now, because angle C is 90 degrees, it means that this triangle is a right triangle. So a right triangle has exactly one right angle in it. It also has two acute angles, but all you need to say is that it has one right angle. So this is a right triangle. And in this situation, we know the lengths of two of the sides of that right triangle, and we are being asked to find the length of the third side. Okay? That is a pretty good indication of how we want to, that's a huge hint in terms of how we're going to go about solving for x in this situation. We have a right triangle, we know two sides, and we want the third side. When you are in that situation, there is a very famous theorem in geometry, arguably one of the most famous theorems in all of mathematics. Students always have a difficult time pronouncing it. It is the Pythagorean theorem. Now, when people think Pythagorean theorem, a lot of people automatically think a squared plus b squared equals c squared, and that's not bad. Okay, that's not bad. I think it's important to understand what the Pythagorean theorem is really saying. And the way that I think about the Pythagorean theorem is I'm going to write a squared plus b squared equals c squared, but I'm not going to write it left to right. I'm going to write it in kind of a weird order because I'm going to write it in the order that we can think about what it's saying. So the Pythagorean theorem says, in a right triangle, the sum, so notice I'm starting with a plus, okay? That's the sum. The sum of the squares, again, I told you I'm going to write this in a weird order. So I started with the plus. It's the sum of the squares of the legs of a right triangle, okay, is equal to the square of the hypotenuse. If you read this left to right, it is in fact a squared plus b squared equals c squared, which I think a lot of us, that's what we think of when we think of the Pythagorean theorem. And again, that's fine. I'm not saying to not do that. But if you think of this as the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse, that's sort of conceptually what it's saying. In a right triangle, the hypotenuse has to be across from the right angle. Okay, so if we're going to use A, B, and C here as our side lengths, then in this case, C has to be 26. Right? You are locked into that, and you don't really have a choice. So the 26 has to be the letter that is by itself in this equation. Now the other two, they're the legs of the right triangle. Okay, which means they're adjacent to the right angle. They're not across from it, but they're adjacent to it. And for these, we can just fill in, it doesn't really matter which one's A, which one's B. So I guess with the way that we've labeled our triangle, we said that this is A and this is B. So A is 10, and B is what it's what we're looking for. It's X. We don't know. So now we just have to solve this equation for x. Well, 10 squared is 100. X squared we can't really do much with at the moment, and 26 squared is 676. 26 times 26. All right, we want to get x by itself, so the first thing we have to do is we have to deal with this 100. Then we're going to deal with the squared, but we have to deal with the 100 first. So that cancels. We are left with x squared equals 576. Now to get rid of the squared, I need to take the square root of both sides. I take the square to the left to get rid of the squared, so I get x. And I take the square root of the right to maintain balance. Now, because we're talking about side lengths here, we do not need to include a plus minus. Right? So we've seen in some context where when you solve an equation like this and you take a square root to like get rid of the squared, sometimes you need the plus minus here. We do not need the plus minus because we're talking about the length of a triangle, and negative length just does not make sense in this context. So we do not need the plus minus. All we need is the positive square root of 576, which is 24. So our answer for 13 is 24. And that is actually all we need. Now, that is the answer to this question. And if you want to move on to the next question, you are welcome to do so. For those of you that maybe want to see a little bit more with this problem, and the reason why you might be interested is because it actually might make your job a little bit easier, which like we're always looking for, right? We always want our job to be kind of easy whenever possible, is that there are certain sets of numbers that are known as Pythagorean triples. And the most common Pythagorean triple, sort of like the most well-known one, is 3, 4, 5. Okay, so this is, like I said, this is a little extra, 3, 4, 5. The reason why this is a Pythagorean triple is that it is a solution to the Pythagorean theorem. If you take 3 squared and add 4 squared, you will get 5 squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, and 5 squared is also 25. So 3, 4, 5 is a solution to the Pythagorean theorem. The reason why this is helpful is that if you have a triangle where your side lengths are 3, your legs are 3 and 4, and you're solving for the hypotenuse, if you can recognize the Pythagorean triple, 3, 4, 5, then you don't need to do the Pythagorean theorem, and you can just say it has to be 5, because that's the Pythagorean triple. Note that you can take any Pythagorean triple and apply a scalar to it. So if you take all these numbers and double them, you'll get 6, 8, 10. That is also a Pythagorean triple. If instead of multiplying by 2, if you multiply by, say, 1/2, right, you'll get 1.5, 2, and 2.5. That is also a Pythagorean triple. And the reason why I'm bringing this up in this problem, and again, this is extra, but you may find it helpful, is that another Pythagorean triple besides 3, 4, 5 is 5, 12, 13. This is another Pythagorean triple. 5 squared is 25, 12 squared is 144. You add them together, you get 169, and 13 squared is also 169. And if you take this Pythagorean triple, and if you double everything, you get 10, 24, and 26. Notice that in our original triangle, we had the audio went out there for a second, we had a leg of 10, and we had a hypotenuse of 26, and our final answer ended up being 24. So Pythagorean triples can make your job a little bit easier if you can recognize them. Not strictly required, but also not a bad idea to get comfortable with them if you're feeling up to it. We'll end this assignment in the Go section, and there's only one question here, but it is clearly multiple points. And instead of reading out like parts A through F and then answering it, we're gonna start by just reading out A. We're gonna do A. We're gonna come back to B, et cetera, et cetera, et cetera, because it's gonna be way too much if we try to tackle this in like one thing. So, 16A. Label points C, E, and D with the correct ordered pairs. All right, well, this is something that we did earlier in Math 1, where we have this figure. It's on the coordinate plane. Each box represents 1 unit, so we don't have to worry about our scale. And part A just simply says label the XY coordinates for C, D, and A. All right, well, shouldn't be too bad. So for point C, we start at the origin. We go 4 units to the left. So that means the coordinates here are going to be -4. I don't go up or down at all. I stay on the x-axis, and so my y coordinate is 0. For point D, again, I start at the origin. I don't go left or right at all, so my x-coordinate is 0. I stay on the y-axis, and then I go up 1, 2, 3, 4 units. So D is at 0, 4. For point E, again, I start at the origin, and I'm going to go to the left 3 units. Because I'm going to the left, it's negative, so it's -3. And then I go up 3 units, and up is positive, so it's +3. So that is my answer for part A. Part B. Translate triangle CED down 4 and right 6. Okay, down 4, right 6. Label the image as triangle C prime, E prime, D prime, and include the new ordered pairs. All right, again, not too bad. We're just going to take each vertex of this triangle, and we're going to go down 4 and to the right 6. Then identify the new XY coordinates. So we'll just go, we'll take, like I said, we'll take each vertex and just do the same translation for it. So we're going to start with C. So for C, we're going to go down 4. And I guess I'll use some maybe like temporary dots here in red. I'll erase these later, but we'll use them for now. So from C, if we go down 4, that brings us to that brings us down to there. That's down 4 from C. And then to the right 6, count them up, 1, 2, 3, 4, 5, 6. All right, well now we are right, not there, that's off the grid. We are right there. So that is my new point C. And I will go ahead and label that as C prime. So C with a little apostrophe above it. And the coordinates for C prime, there's a couple different ways that we could get the coordinates for C prime. One way to get it is to just treat it as like a brand new point and just start at the origin and go from the origin to C prime. So if we start at the origin, we're going to go to the right 2, so it's +2. And then we're going to go down 4, so our y coordinate would be -4. So our coordinate for C prime is 2, -4. Notice, however, that there is an alternative way that we could have gotten C prime, and that way is to relate it to C. So remember that from C to C prime, we went down 4 units. Well, notice that my y coordinate here started at 0, and then I went down 4. Well, 0 minus 4 is -4, which is the y coordinate for C prime. Similarly, for the x coordinate, I started at -4, and then I went to the right 6. When you go to the right, you're adding 6. So -4 plus 6 gives me +2, which is my x coordinate. So again, to get the coordinates for C prime, you can either get the coordinates like you would for just any point and just start at the origin and then go. Or you could start at C and apply the translations to the coordinates themselves, and you will get that as well. That can be very helpful if you're not given a graph. So you may have a situation where you're doing this problem, but you don't have a graph and you can't visually sort of see where it ends up. So in that case, actually manipulating the coordinates themselves may be preferable. We no longer need that red point there. We're going to do the same thing to point D. So we're going to start at 0, 4, and we're going to go down 4. That actually brings us to the origin. That's our temporary point. And then we also want to go to the right 6 units. So from the origin, if we go right 6 units, that brings us to there. And we're going to label that as D prime. And again, no matter how you get it, whether you start at the origin and go to d prime, or if you start at d and go down 4 into the right 6, no matter how you do this, you will get the coordinates of 6, 0. So whichever method sort of makes more sense to you, feel free to use that. But in any method, d prime, you should be getting 6, 0. For e prime, we're going to start at e, which is at negative 3, 3, and we're going to go down 4. So that brings us to there from e. And then if we go to the right 6 units, well, going to the right 6 units brings us to right there. And that is e prime. So that's e prime. And my coordinates here are, again, no matter how you get there, it's 3, negative 1. And that's it for part B. That's it for part B. So we can actually stop there before we go into part C. So part C says draw the line segment CC prime, the line segment EE prime, and the line segment DD prime. What is the slope of each of these line segments? Okay. Actually, I lied. The directions did not say. I don't think it said to connect. No, we do. It's because we're translating the triangle, so we do need to connect the points. I was being a little bit of a stickler, but yeah, it says translate the triangle, and by translating the triangle, it means we need to include all of the points. So we actually do need to connect these. I thought that was going to be in the next step, but we should have already done that. So that. All right. That is our answer for part B, is the actual triangle itself, not just the vertices. Now, part C says to draw, I'll do this in green, I guess. So it's to draw C to C prime. So I'll go ahead and do that. So that's C to C prime. It also said to draw D to D prime, like that. And E to E prime, like that. Okay. So the other part in part C was, what is the slope? All right. Well, I don't want to spend too much time on this. We could use our slope formula, y2 minus y1 over x2 over x1, but we're given a graph, and I just think it's going to be easier if we just sort of just visually look at them. So the slope for we'll just call it C, the C to C prime line. So going from C to C prime, we are going to, well, we're going to do what we did with our translation, right? To go from C to C prime, we went down 4 and to the right 6. So when we do our slope is going to be rise over run, our change in y over our change in x. Well, pretty much by definition, the change in y going from C to C prime, again, remember, we went down 4. So that is my change in y. And then my change in x, again, we went to the right 6. So that means we went positive 6. So my slope for line C, for CC prime, is going to be negative 4 over 6. When you have a negative over a positive, you really should pull the negative out and make the entire fraction negative. And then we've got 4 sixths. 4 sixths reduces to 2/3 because they both the numerator and denominator have a factor of 2 in them. So we can factor that out, and we're left with negative 2/3. Well, that's for C to C prime. I don't think it's too difficult to see that if we do D to D prime, we're going to get the same result because we applied the same transformation to D that we did to C. Every single point here, we went down 4 and to the right 6. We did that for C, we did that for D, we did that for E, and really we did it for every point also on the triangle, not just the vertices. Every single point went down 4 and to the right 6, which means every single line, not just the C line, but every single one that we just drew is going to have a slope of negative 2/3. So our correct answer, let's see, is there a spot? Yeah, I guess we have to just write it down here. So our answer for C is that the slope of every single line is negative 2/3. So that's our answer for C. Part D, reflect. Okay, so this is a different transformation. So this now says reflect triangle C prime, E prime, D prime across the y equals 0 line. Label the image triangle C double prime, E double prime, D double prime. Include the new ordered pairs. All right, so we're going to create another triangle, this time double prime. And in order to do that, we're going to reflect across the y equals 0 line. So again, this is a reflection. And we're taking our image, not the original, right? So the most recent triangle that we drew, and we're going to reflect it across the y equals 0 line. Okay. So the line y equals 0 is the x-axis. So the equation of the x-axis is y equals 0. Which hopefully makes somewhat sense because on the x-axis you're not going up or down at all. Y is 0. So that's why that's the equation. And what we're going to do is we're going to reflect our most recent triangle, the one that's like to the bottom right, and we're going to reflect it across the line y equals 0. When we're doing a reflection, the way that we want to do that is we want to, if we're going to reflect C prime, right here. Okay, we're going to start by reflecting that line. The way that we want to do that is we want to count the boxes that it takes to get to the line that we're reflecting across, which in this case is the x-axis. So if we count the boxes and we get to here, that is 4 boxes to go from C prime to that dot right there. We went up 1, 2, 3, 4. What that means is we're going to now continue to go in the same direction, to go up, and we're going to go the same amount. So from here, if we go the same amount, which was 4, we end up right there. So that point, that black point that I just drew, we'll get rid of the red, but that black point is our C, hold on. So that is C double prime. And the coordinates for C double prime, well, we go to the right 2, which makes sense because we didn't change our horizontal distance at all. But whereas C prime was negative 4, C double prime is positive 4. Okay. Now for D, notice that D is on the x-axis. It's on the line y equals 0, which means my distance from D prime to my line, my reflection line, is 0. So I don't go any boxes. I don't move any boxes, and then I don't move any boxes again. And essentially, it ends up turning out that D prime and D double prime are the same point. Right? So that point right there has essentially 2 names. It is both D prime and D double prime. They overlap. All right, well, that was easy. E prime, again, we want to figure out, all right, how far is this point from my reflection line? And E prime up to the x-axis is 1 box. That gets us to here. So because we traveled 1 box, we're going to travel 1 more box. It's going to be the same distance, and that puts us at right there. Okay, so that point that I just drew is E double prime. And the coordinates for that point are 3, which again should make sense because E prime was 3 and I didn't move left or right at all. But E prime was negative 1 and now E double prime is positive 1, just like that. And again, I want to connect all of my triangle vertices here. So C to D is going to look like that. D to E is going to look like that. And E back to C is going to look like that. Okay. We have reflected triangle C prime, E prime, D prime over the line y equals 0, which happens to be the x-axis, and we have obtained a new image that is triangle C double prime, E double prime, D double prime, which is basically in the first quadrant. All right. We've done all of D. Good. Now part E. Draw line segment C prime, C double prime, and line segment E prime, E double prime. Why don't you need to draw D prime, D double prime? What is the relationship between C prime, C double prime, and E prime, E double prime to the line y equals 0 line? All right, so we got a couple things we got to do here. So I'll do this in red. So we're being asked to draw the line segment that starts at C prime and goes to C double prime. All right, well, that's just going to look like, I don't want it to be a thick line. One of these days I'm going to stop doing that, but that day is not today. So C prime to C double prime, that line segment looks like that. And then E prime to E double prime looks like that. So those are my two line segments. Now, the question said, why don't you need to draw D prime, D double prime? So we have to answer that. So part D here, the reason why we don't need to draw D prime, D double prime, so D prime and D double prime coincide. So you can't draw, it's one point. There's no space in between D prime and D double prime, and you can't draw a line segment that's a point. Those are two different things. A line segment is different from a point. So D prime and D double prime coincide. That's why we can't draw it. And then for also, oh no, this is part E, sorry. So not D, this is E. So part E. The other part of part E said, what is the relationship between the two red lines that I just drew and the line y equals 0? So both of my red lines are vertical lines, and the line that I reflected across was y equals 0. So what's the relationship between the horizontal line that I flipped across and the vertical lines that I just drew? Well, they pretty clearly form a right angle. So what I'm just going to say here is that the lines in question are perpendicular. You know, we're kind of taking some time on this problem, so I'm just kind of giving a pretty succinct answer here. But the lines in question that we're talking about are perpendicular. So the red line is perpendicular to y equals 0. Both red lines are perpendicular to y equals 0. Okay. Last part here, part F. Rotate triangle CED 180 degrees about the point -2, 0. Label this image as triangle C triple prime, E triple prime, D triple prime, and include the new ordered pairs. Okay, so now we're rotating the original triangle, not any of the images, but the original triangle. We're going to rotate it 180 degrees about the point -2, 0. Okay, so the point that we're going to rotate around, I should probably use a new color here, orange. We'll try orange. So -2, 0 is right there. Let's be careful here. Don't erase all that. All right, it's right there. So what I want to do is I want to take my original triangle and I want to rotate all of my points 180 degrees around that orange point. So in order to do this, what I'm going to do is I'm going to take each vertex. I'm going to see, all right, well, what's my journey to go from the point to my orange point? So for C, what I'm going to do is I'm going to start at C and I'm going to go to the right 2 units. That gets me to orange. What that means is when I rotate this, I'm going to do the same thing. So I'm going to go 2 more units to the right. Yeah, we'll stick with orange. Why not? So that means that C triple prime is going to end there because, again, I went from C, I went, actually, I should not use orange. It's going to get confusing. I'll just go back and use black. So that gets me to there, which is C triple prime, which is the origin. All right. To get D triple prime, I am going to, again, I'm going to ask myself, how do I go from my original point, which is there, that's where D is, how do I get to orange? Well, the order doesn't really matter here, but I'm going to go down 4 and to the left 2 to get to orange. What that means is if I'm going to rotate 180 degrees, I do that same thing again from orange. So I'm going to go again from orange, I'm going to go down 4 more and left 2 more. I repeat the journey. So from orange, if I go down 4 and to the left 2, that brings me to there. And that is D triple prime. And the coordinates there are -4, comma, -4. So that's D triple prime. Same thing with E. I'm going to start. That. Okay. I'm going to start at E. I'm going to say, all right, how do I get to orange, right? So from E, I'm going to go down 3 and to the right 1. So if I do the rotation from orange, I'm going to do the same thing. From orange, I'm going to go down 3 to the right 1, and that gets me to right there. And I can go ahead and label that point as E triple prime. And the coordinates there are -1, comma, -3. And we're kind of encroaching on some other points here, but I think it's good enough for right now. And the last thing I have to do is just connect these points. So C triple prime to D triple prime is right there. D triple prime to E triple prime is right there. And E triple prime back up to C triple prime is right there. And that triangle has now been rotated 180 degrees around that orange point. And if you look at it, it should look like it's been rotated. And I think that is it for question 16.